right, and I'm starting our video. All right, so this is where we were last class. We had just started talking about this idea of a crystal lattice. So when we have a solid ionic compound, it is a crazy semester. When we have a solid ionic compound, we have our ions and they are essentially stuck together in this solid. Now, we're pretty used to throwing that solid into water and mysteriously, magically, they all dissolve, and we'll talk about why that happens in our last chapter this semester. But right now what we're talking about is these ions separating without water. So we're talking about the idea of ripping these ions away from their partner. So once upon a time, way back when, I told you ionic compounds aren't truly bonded. They are just attracted to each other. And you're thinking, hey, I could tempt that sodium away from the chloride. I'm cool enough. Well, it's not that easy. To pull these two apart, you need extraordinary amounts of energy. So once upon a time, I told you it's over 1,000 degrees Celsius to separate sodium chloride without water. So now what we're going to take a look at is called our lattice energy. It's lattice energy. And the idea of the lattice energy is, let's say you are this mean, cruel homewrecker and you want to pull these ions apart. How much energy do you need to do that? And that's what we're going to be calculating. I know we're horrible, cruel people. So again, our crystal lattice, it's a three-dimensional array, and the ions are in that regular array. So just to take a look here, this is a simple crystal, and we have just sodium and chloride. So here is our sodium, chloride, sodium, chloride, sodium, chloride, sodium, chloride, sodium, chloride, and so on. So it is a three-dimensional array, and this can extend infinitely. So if you've ever gone to a cave, you've gone on a cave tour, and you see these giant crystals, they're growing from the ceiling, they're coming up from the floor, those are ionic compounds. So if you give them enough time, they will just grow and grow and grow. And if you know some geology teachers, there's several of them who have a little project, whether it's at home or in their classroom, and they're trying to grow the biggest crystal ever in the world, and they may have started it 20 years ago. Truthfully, they're never going to match the ones in caves because those have been growing for hundreds of years, if not thousands of years. But they often have that little project to see how big they can make their sodium chloride. I think the biggest sodium chloride that I've ever seen was maybe a foot or two long, and that was by a geology teacher just trying to see the best sodium chloride he could grow. But this can be done with any ionic compound. And just a note, the lattice that we're looking at right here would be termed a perfect crystal. So it's a perfect crystal because it is in perfect shape, and that's how we're going to assume our lattices are, our ionic compounds. So by perfect, I mean everything is lined up properly. So here's the sodium, the chloride, the sodium, the chloride, the sodium, and there's going to be a chloride in there, down there somewhere. So nothing is out of place. It is always possible to have something slightly out of place. Life happens. Sometimes things don't fall exactly where they're supposed to. And when that happens, the lattice energy actually gets lower because it's a lot easier to separate them if they're not put in their proper place. But again, we're going to assume here that we have a perfect crystal. Everything is perfectly aligned. Okay, so questions about anything here for the crystal lattice? And again, every ionic compound, when it's in its solid form, we assume it to be in this crystal lattice. All right. Trying out a new webcam today, and it seems like everything's just a little fuzzy in my image, but that's okay. You guys already know what I look like. All right. So here, again, are ionic compounds. Formation of an ionic compound can be very exothermic. So when we say it's exothermic, it's giving off a lot of heat. So when it gives off a lot of heat, what we're saying is it's going to a much more stable configuration. So our solids are very stable. It's one of the reasons they can drive a chemical reaction. Once upon a time when we were doing our net ionic equations, we said that if you can form a solid, liquid, gas, weak acid or weak base, then your reaction is going to happen. And that's because those are energetically favorable. Another way of saying that is that they give off energy. They are exothermic when they happen. And that is very true for NaCl. So I think the last thing we looked at last class was the video of sodium plus chlorine gas forming NaCl. So if you missed that last class, feel free to Google that. There's tons of videos on YouTube about that. So now let's move on to our lattice energy. So our lattice energy, also referred to as Le or delta H lattice. Here it says the energy given off when 1 mole of solid crystal lattice forms from gas ions. So there's two ways of talking about this. Your textbook talks about it as the formation. So it's talking about it as an exothermic event. It's talking about when these beautiful young ions get together and plot their life together. So sodium and chloride get together and all this energy comes off. But there's another way of talking about it, and it's the way I've been referring to it because I think it's a little easier to kind of conceptualize this way. And that is, how much energy does it take to rip them apart? I'm a mean, horrible person. That's why I think of it that way. Just because I think people understand it a little bit more when you think of how much energy is required to rip it apart. But again, your textbook does refer to it as how much energy is given off when they get together. Either way is fine with me, and what that means is for delta H lattice, you can refer to it as positive or negative because depending on the textbook, some will refer to it as positive when they're thinking of ripping them apart, and some will refer to it as negative when they talk about the ions getting together. So in order to talk about lattice energy, we have to talk about electron affinity and ionization energy. So we did this probably a couple classes ago. So let's start off with our electron affinity. So we said electron affinity is a measure of how fond something is of electrons, how much it wants those electrons. So it always involves gaining the electron, and energy will always be released, and we always produce an anion, a negative ion. So this is about taking in an electron and giving off energy. And that is our electron affinity, which we also refer to as EA. So next up we have our ionization energy, which we also can refer to as IE, and it involves losing an electron. Here energy is always added and a cation is always produced. So for example, if we were to say chlorine and we were to steal an electron away, it would end up being positive and we would have to put energy in. So these are really similar terms, and that's why I made this PowerPoint, just to kind of give you an idea, comparing them, how they're similar and different. So one of them is about taking an electron in, that's your electron affinity. One of them is about giving off an electron, that is the ionization. So whenever you rip an electron away, you always have to put in energy. Whenever you give an electron, you're always going to get energy out. So any questions about the difference between the electron affinity and the ionization energy? Okay. Let me just move a window over here. There we go. All right. So next up, we are going to calculate the lattice energy of NaCl, giving the following data. And now I want to remind you of something we talked about a while ago. And I told you when we were doing electron affinity and ionization energy, we talked about the electron either being given off or taken in the gas form. Even though that's not always the way it happens in the lab. That's the way we calculate it. That's the way we talk about it theoretically. So here we're going to say we only transfer electrons in the gas state. And again, that's theoretical. That's not in the lab. In the lab, it is absolutely possible to transfer them without being in the gas state, and normally we do transfer them when they're not in the gas state. All right, so here I do need you to show states, solid, liquid, or gas, on the lattice energy calculation problems. All right, so first of all, there's a couple ways to do this. One is called the Born-Haber cycle. What I found is a lot of students aren't thrilled with the Born-Haber cycle, so I do this based on good old Hess's law, which I know a lot of people aren't thrilled with Hess's law either. Oops, sorry, we got a cat visitor. This is little Karma. Okay, so we are going to do the Hess's law version. However, for those of you thinking, hey, I'd like to see this again, maybe in a different way, I'd like to see the Born-Haber cycle, I have a video link to our websites in the video section, and some students find that helpful. All right. So let's go ahead and take a look at how to calculate this. So we are calculating the lattice energy of NaCl. And I'm going to do this in terms of taking these ions away from each other, ripping them apart rather than putting them together. Because again, I think it makes a lot more sense to think of it as how much energy do I need to tear them apart than how much energy do we need to put them together. So here we're going to make NaCl solid, and we're going to do it from our gaseous ions. So again, the reason we're using gases is just by definition. If you were in the lab, you would not necessarily need gases. So here is Na plus as a gas, and here is Cl minus also as a gas. This is what your textbook calls delta H lattice, but I'm going to go ahead and rewrite this, and I'm going to say NaCl as a solid, breaking up into Na plus gas, plus Cl minus gas, and I'm going to call this negative delta H lattice, because I just flipped that equation around. So again, I'm just doing this because I just think it's easier to conceptualize this way. And let's see, I see a question coming in. Outside of the lab, why is it only calculated in a gas? That's a good question. So I know it is done by definition, but I would have to look and see why they decided to do it that way. It is a way they've done it for hundreds of years, but I would have to take a look and see why they decided to use gases. That's a good question. All right, so next up, what I want to talk about is our delta H of formation. So we saw this once before. We talked about how to form something from its standard states, but I'm going to do it just slightly different, and I'm going to call it negative delta H of formation. So now I'm going to take that sodium chloride, and I'm going to break it up into its standard states. So what's the standard state of sodium? What is its natural state? Is it solid, liquid, or gas? Excellent. So I'm seeing lots of solids come through. All right, so normally sodium is a solid. And how would we normally find Cl? Solid, liquid, or gas? Excellent. And do we find it just the way I've written it here, just a lonely Cl all by itself? Excellent. So I'm seeing Cl2 because it is diatomic. So here, if we're talking about the delta H of formation, how we would form them is from sodium metal and chlorine gas. And to balance this out, I'm going to put a 1/2 here. So we only want to talk about 1 mole of NaCl like so. All right, so any questions on anything here so far? All right, so now what I want to do is think about what we've got. We have sodium as a solid, and we have 1/2 Cl2 as a gas, and somehow I need to turn them into sodium as a gas and Cl minus as a gas. So I'm going to start off talking about the sodium. All right, so right now we have this sodium right here. So this is Na as a solid. But somehow I need to turn it into sodium plus as a gas. So the first thing I'm going to do is turn it into a gas. And we talked once upon a time about going from a solid to a gas, and we called it sublimation. So there is a delta H sub, and that is delta H of sublimation. However, we can also say that this is delta H of formation for Na as a gas. And that is because to make Na as a gas from its standard state, we would make it from sodium solid. So any questions about what I just did by turning sodium as a solid into sodium as a gas? All right, so next up, we need to turn this sodium as a gas into sodium as a gaseous ion. So I'm going to take this right here and say Na as a gas. I really want it to be Na plus as a gas. So the only way you can make something positive is to remove an electron. And I'm going to put it here on the product side because it's being removed. It's going somewhere else. So here, this we can call our ionization energy. Or we talked about it in one other way, and we called it I1. I1 because it is the first ionization energy. We are removing the first electron from sodium. If we were going to go on and make it a 2 plus, then we would have I2 as well. But here we're just taking the first electron off, so that is I1. So any questions on what we've done so far? All right, so let's just review. We wanted to take this solid sodium and turn it into a gaseous ion. And let's take a look at if we've done that. So here, we can cancel out sodium as a solid. We can cancel out sodium as a gas. And there's that gaseous ion that we wanted. So this is Hess's law. I'm crossing out things that we see on the right side and again on the left side. We're going from sodium as a solid to sodium as a gaseous ion because we need that gaseous ion right up here. So any questions on anything so far? All right, so next up, let's take a look at our chlorine. So here is our Cl2, and we have 1/2 Cl2, and we need to turn it into Cl minus. So it's already in its gas form, but we actually have to break a covalent bond. Those Cl2, the 2 chlorine, they're bonded together, and we need to break that up. So we have 1/2 Cl2 as a gas. And it's going to go on to Cl as a gas like so. And we've talked about those chemical bonds once upon a time. We looked at these average bond energies, so we called them delta H bond. We also called them D for the bond dissociation. So I can refer to this as 1/2 delta H bond. I can also refer to this as 1/2 of D, the bond dissociation for Cl2. And we have one more thing that we can call it. Let me squish this down a bit. And that is, let me just go into the next line. Delta H of formation for Cl as a gas. So we are forming Cl as a gas from its standard state, and its standard state was right over here. Cl2 is a gas. So all 3 of these right here describe what we're talking about. So you can talk about them as 1/2 of delta H bond, 1/2 coming from right over here. We could talk about 1/2 of the bond dissociation, again 1/2 coming from right over here. And then finally, the delta H of formation, talking about this chlorine right over here. So questions on what we've done here, essentially taking our Cl2 and breaking its chemical bond. All right, so next up, we need to take this Cl as a gas. It's now just a lonely Cl all by itself, and we need to make it an ion. So I'm going to say Cl as a gas goes on to Cl minus as a gas. And the only way something that's neutral can become negative is to take in an electron. All right, so Cl takes in that electron, And this is something that we called electron affinity. Let me move this down a line to get some room. This is our electron affinity. This is going to measure how much energy is going to come off when chlorine takes in that electron. So any questions on anything so far that we've done? All right, so now let's take a look at what's going on. So we started off with 1/2 Cl2 as a gas, and here it is. We can cancel this because you see one on the product side, one on the reactant side. Then we have Cl as a gas, and I can cancel that right over here because we have one on the product side, one on the reactant side, just like we've done in Hess's law. And we are left with Cl minus as a gas, which is exactly what we want. We then have one more thing that we could cross out, and that is the electron. So sodium gives up an electron, chlorine takes in that electron. That's our redox reaction. And so now what we have is NaCl solid that we started with, and we have produced sodium as a sodium gaseous ion and chlorine gaseous ion. So let's write that out. So NaCl as a solid going over to Na plus as a gas plus Cl minus as a gas like so. So this is the equation that we come up with. And if we compare it to way back when, this is, you can think of it as the delta H lattice or the negative of delta H lattice, depending on whether you want to think about the ions being torn apart or put together. But this is the equation we were shooting for. And this is the equation that we have. So we have done our Hess's law correctly. And now we're going to be adding up our values. But before we add up those values, any questions about anything that we've done here? Okay. All right, so now let's get our values. So for the first part, we're going to need the negative of delta H of formation. Here's our delta H of formation. It is negative 411.2. According to our equation, we need the negative of that. So negative delta H lattice equals negative of, I forgot already, I think it's 411. Yep. All right, so negative of negative 411.2, and most of you are like, duh, that's a positive, but I just wanted to write it out so everybody could see what we're doing. Next up, we need either the delta H of sublimation or the delta H of formation for sodium as a gas. And what we're given, delta H of formation for sodium as a gas. So 108 kilojoules. So any questions on what I've written so far? All right, so next up we need our ionization energy, also known as I1. And here it is right here. This is I1 for sodium. So 496 kilojoules. Make sure I grab that number correctly. Yep, 496. Any questions on anything so far? Make my 6 a little more presentable. There we go. All right. So those are the 3 numbers that we have so far. Now let's move on. Yes. So the only time I could think of it not being provided would be if we're given everything else and you were just asked to solve for the ionization energy. That would be the only time it wouldn't be provided. So in that case, you'd actually be given the lattice energy, but I'm not sure if I've ever asked a question like that. That's kind of tricky, and it's already a tricky question. But if you're asked to find the lattice energy, then you would have to be given the ionization energy. All right, so next up is our chlorine. We either need 1/2 for delta H bond, 1/2 of the bond dissociation, or the delta H of formation for chlorine. And here we're given the delta H of formation for chlorine as a gas, and it looks like it's 122 kilojoules. That's delta H of formation for our Cl as a gas. Questions on anything there? Okay, we're almost to the end here. So next up, we have our EA, our electron affinity. And here's that electron affinity. It is negative 349 kilojoules. And these are the values that we're going to add up. So any questions so far? All right, go ahead and take a moment and add all of these up. Once you get your value, feel free to type that into the chat box. In terms of the order they're placed in, since this is addition, you could really add them in any order. Good question. All right, so it looks like Andrew got 788 kilojoules, and it looks like Allie did as well. How about the rest of you? Looks like Tasso's getting something similar. Excellent. And Jury, excellent. Excellent. Looks like Kimberly got something similar. And Jessica, excellent. All right, so I went ahead and put up that poll. So go ahead and click in if you'd like some more time or if you're ready to go over it. All right, so only 64% of you voted, but everybody that has voted says that they're ready to go over it. Okay, so let's go ahead and go over it. So it looks like adding this up, y'all are getting 788 kilojoules. So this is your delta H lattice. So this is the amount of energy that you would need to rip the sodium and chloride apart, or you can think of it as the amount of energy that will be given off when they get together. And it is 788 kilojoules per mole. So any questions on what we did here?
Yes. Looking in the negative H lattice, is that the same thing as the negative H formation?
Oh, you know what? I wrote delta negative H lattice, and I should have said negative delta H of formation for NaCl solid. Sorry about that. I wrote it wrong there. So this one should have been negative delta H of formation for NaCl solid. Thank you. All right, so
we don't use the negative H lattice.
that's actually what we're finding here. So I don't think,
Oh, okay.
yeah, we weren't given that because that's what we were actually calculating. So again, for this one, you can report it as positive or negative because it depends on which definition of lattice energy you're using. Okay, any questions on anything here? Okay, so if I were to ask you to do this on a test, I would ask you it in the problems at the end where you could show me all your work. And you have two options for showing me your work. You could show me the Hess's law, which you see right here, or you could show me the Born-Haber cycle, and the Born-Haber cycle is linked in that video. So again, most people find Hess's law a little easier, but some people prefer that Born-Haber cycle, so either one is fine, but you do need to show me all of the equations with the states if I asked you to do this on a test. So any questions on anything so far? Okay. So next up, we are going to compare lattice energies. So it says look at the charges on the ions first. The greater the charge of the ions, the greater the lattice energy. So the greater the charge, the more traction they're going to have, and the more energy is required to break them apart. So way back when we talked about these ions are only together because they are attracted. We called it electrostatic attraction. So there's no true chemical bond. It's just how much they like each other. So if we were to look at something like sodium and chlorine, it has a 1 plus and a 1 minus. So they are very fond of each other. However, calcium has a 2 plus and sulfur has a 2 minus. So you could think of them as calcium and sulfur being drawn to each other twice as much. So the plus 2 and the minus 2, when we have those greater charges, they are drawn to each other even more. What that means for our lattice energy is if you're going to try to rip them apart, you're going to have to put in a lot more energy because they are more attracted to each other. It's an electrostatic attraction, but it's still attraction. So they are much more attracted to each other and they do not want to come apart. So whenever you have ions with a larger charge, you will have a greater lattice energy because they are going to resist being pulled apart because they have a greater attraction to each other. So any questions about that so far? Move the sound box. Oh, Jessica, is it my speaker that's causing problems? Okay, let me try one more thing. Right. Let me try just talking a little louder. All right. Is this any better? Is this better than before? Or can you not hear me at all now?
No, Professor, we hear you.
Oh, okay.
Your sound bar's on the screen now. The sound bar.
Oh, the sound.
Underneath where we can't read NaCl.
Oh.
Underneath.
Okay.
Oh. There you go. There you go.
Okay. Let me just see what's going on. Oh, is it this bar right here?
We can't see what you typed in the other.
Okay. Let me just change my share here. Hold on one sec.
We can hear you though.
Oh, okay. I see. I see what you're saying. I thought it was this little.
No. The sound is fine. It's the bar that comes underneath on the screen. We can't read.
Okay. Okay. So I changed my share, so I think it's not going to do that anymore. I'm hoping.
Okay.
But if it does, let me know though.
Okay.
Excellent. Thank you for letting me know, both of you. All right. So any questions about the idea that the sodium and chlorine will not be as attracted to each other as the calcium and sulfur, and that the calcium and sulfur would have a greater lattice energy because they're more attracted because they have higher charges? So the question was, which of the following has the greatest lattice energy? And it is definitely going to be the calcium and the sulfur. They are much more attracted to each other, which we see in those higher charges. So any questions on anything so far? All right, so next up, when we're comparing our lattice energies, when the charges are the same, we're going to look at the size of the ions. So we can only do that though once we have the same charges. So let's go ahead and take a look at these, and actually let me give you a minute to write them down because I know I added these on right before class. So go ahead and take a moment to write all this down if you would like. Okay. So, did I hear a question starting? Or? All right, so let's go ahead and take a look at their charges first. So magnesium has a charge of +2 and chlorine of -1. Then calcium is +2 with bromide being -1. Strontium is +2 and iodide -1. So we're never going to look at their sizes until we've checked their charges and they all have the same charges. So in our next example, we'll see a kind of a mixed example where we have different charges and different sizes. But for right now, we're going to look at things that all have the same charges. But again, you don't get to move on to start looking at the charges until, to move on to looking at the sizes until first you've checked all your charges. All right, so these all have the same charges. So now we get to look at their sizes. And I want to remind you of our sizes on the periodic table. So what we said is we get smaller going up and smaller going across. So way back when we looked at fluoride and rubidium, which we called real big, but the trend goes throughout the periodic table. So we really see our smallest right over here and our largest over here. So let's take a look at these right here. So it says, which of the compounds will have the largest lattice energy? So let's go through and highlight these. So here we have magnesium and we have chlorine. Then we have our calcium and we have our bromine. And finally we have our strontium and we have our iodine. And we said that we are smaller here and we are larger here. So over here we want to know which one has the largest lattice energy. All right, so what do you guys think? Which of these pairs will have the largest lattice energy? All right, so I'm seeing SRI. Excellent. So I'm seeing SRI from a lot of you. And let's take a look at what our rule is, though. So our rule is going to be the smaller the atom, the greater the lattice energy. So let's go back. We're looking for the smallest atoms. So which one has the smallest atoms? MgCl2, yes. So MgCl2 actually has the smallest atoms. And we've talked before about fluorine being small but mighty, and this is another example of the tiniest atom winning. So it is the smallest atoms here that are going to be the strongest in terms of lattice energy. And the reason is they sit close together. So if you have two large atoms, their nuclei actually sit further apart. There we go. And if you have small atoms, those nuclei sit very close together. The closer they are together, the harder it's going to be to rip them apart. So what we're going to see is the smaller the elements, have the larger lattice energy. So again, if you can think about our discussion on fluorine, remember we said fluorine was small, but it was mighty. Same thing here. It is the smaller elements that are going to have the greater lattice energy. Okay, so questions on anything here so far? All right, so when the charge is the same, again, that's when we're going to look at the size of the ions. So the smaller elements will have the greater lattice energy. So let's take a look at how this works. So here, the lattice energy is proportional to the potential electrical energy in a compound. So this EEL is actually our potential electrical energy, but it is proportional to what we're looking at for lattice energy. So up on the top, we have our charges. We also have a constant K. And then down at the bottom, we have D, which is the distance between the nuclei. So what we see is that the greater the charges, the greater the lattice energy, but the greater the distance between these nuclei, the smaller the lattice energy. So this is where we get our rules from. So larger charges equals larger lattice energy. But because that distance is down at the bottom, what we see is the smaller atoms have the larger lattice energy. And again, this should make sense if you kind of think about it, that the greater the charges, the more attracted they are to each other and the harder it's going to be to pull them apart. Same thing for those smaller atoms. They are sitting closer together, and the closer together they sit, the harder it is for us to rip them apart. So any questions on this idea so far? Okay, so I just wanted to give you sort of a mathematical basis for what we're talking about. So you don't need to be able to solve the equation or even remember the equation, but I want you to understand it in the sense that this is just giving you more background about why the larger charges give you a larger lattice energy and why the smaller atoms will result in a larger lattice energy. So this is just a mathematical background for that, for those of you who love your physics and you love seeing the mathematical relationship behind it. But again, I'm not going to test you specifically on that equation. But any questions on anything here? So here it says when the charges are the same, that's when we look at the size. So charges are always more important. So smaller atoms will have the greater lattice energy. The smaller they are, the closer they physically are, and the more energy is required to break them apart. So let's take a look at this set down here at the bottom. And if I were to put in the charges, sodium is a positive, chlorine is a negative, cesium is a positive, iodine is a negative, potassium is a positive, bromide is a negative. So here we have three that all have the same charges. Sorry. All right, so let's bring these down. I feel like I'm having technical issues everywhere today. All right. All right, so these are our three ions, and the question is to arrange them in order from least to greatest lattice energy. All right, so let's start with the sodium chloride. So here is sodium and here is chloride. And next up, cesium iodide. And finally, our potassium bromide, like so. All right, so we want to order these from least lattice energy to greatest lattice energy. So just take a look at where they are on the periodic table. Which one of these ionic compounds is going to have the greatest lattice energy? All right, it looks like Clinton's made a suggestion of cesium, then KBr, then NaCl, and it looks like Jervin is agreeing with the NaCl for the greatest lattice energy. What do you all think of NaCl for the greatest lattice energy? Excellent. And I think Clinton made a suggestion about it before. What do you all think about for the least lattice energy? Which one will have the smallest lattice energy? Excellent. So cesium iodide, also known as CSI, and that puts KBr in the middle. Excellent. All right, any questions about how we ordered these? All right, so again, the only reason we could compare their sizes is because they all have the same charges. There's a strange periodic table. There we go. Yep.
Could we prioritize the charge of the ions before we start checking the size of the ion?
Exactly. That's exactly what you want to do. And the reason is because the charges are essentially twice or even the square of importance, because we have both of the charges up on the top, and there's two of them, so they do become more important than the size. So yes, definitely prioritize the charges over the size. All right, so here it says which ionic solid has the greatest lattice energy, and let's get a periodic table while you guys are working. All right, so I want you to give this a try. The greater the charge, that has priority. Okay, so I see a question about what if you had sodium iodide and cesium chloride. So in that case, you would need more data for that. So I wouldn't give you a problem where they're sort of opposite, where one, like the cation in this case, is smaller and the anion is bigger. So I wouldn't give you one like that because you'd need more data to figure it out. Good question, though. So his question was, what if you had sodium iodide and cesium chloride, where sodium was the smaller of the cations and chloride was the smaller of the anions? But go ahead and take a couple minutes and try to figure out which one would have the greatest lattice energy. Once you feel confident with your decision, feel free to put it into the chat box, or put it in the chat box even if you're not confident. All right, so it looks like Jervin has MgO. How about the rest of you? What do y'all think? All right, so I'm seeing a lot of MgOs coming through. Excellent. All right, so I went ahead and put up the poll again, so go ahead and click in if you are ready to go over it, if you'd like more time. It looks like everyone who's brave enough to click in is ready to go over it. I'm going to assume the other two people stepped away from their computer. All right. So the first thing I'm going to do is put in the charges, because the charges are more important. So potassium is a positive, chloride is a negative. Barium is a 2+, sulfur is a 2-. Strontium is a 2+, sulfur is a 2-. Sodium is a plus, chloride is a negative. Magnesium is a +2, and oxygen is a -2. So first of all, any questions on how I assign those charges? All right, so the next thing, we are only interested in the compounds with the largest charges because we want the largest lattice energy. So I'm going to go through and slice out anything that couldn't possibly be our answer. So the greatest lattice energy will always belong to the compounds with the largest charges. So any questions on why I crossed out A and D and why they're not it's not possible for them to be the correct answer? Okay, so now let's go through and find our compounds. So we have barium sulfide. So here's our barium, and here's our sulfur. And then we have strontium, and we again have sulfur. And finally we have magnesium, and we have oxygen. So here we're looking for the smallest elements, and our trend was going up, and going to the right we get smaller. So the smallest ones are indeed magnesium and oxygen. So E is our answer, magnesium oxide, which you guys already knew and you totally didn't even need me. So magnesium oxide is our answer because it has the largest charge between -1 + 1 and -2 + 2, and it has the smallest size. So greatest charge and the smallest size. But again, the charge is more important than anything else. Okay, questions on anything here?
How is something like let's say NaS with a +2 and a -1, or like NgCl where there's like a +2 and just
So you're thinking, I think I heard an NaS, and then what was the other one? Or do you want to just look at that NaS?
like an NaS and an NgCl2.
NgCl2. So
How would they fit?
oh, sorry, say that one more time.
How would they fit in between like a plus negative and a 2 + 2 negative?
Okay. So here we've got a +1 and we have a -2, and here we've got a +2 and a -1. So if we were to go back to that equation for the electrical charge here we would have a +1 and a -2, or we could have a +2 and a -1. So that is a smaller difference in charge than if we had a +2 -2. So what I would say in terms of where they would fit, let's say we just had a series that was, let's rank these just by charge. And we have our NaCl, and we have our Na2S, and we have our, let's say, SRS. So the +1 -1, +1 -2, and +2 -2. So this would then be the largest lattice energy. This one would be the smallest. And this one right here would end up in between because it has one that's a 2- and one that is a +1. So is that sort of your question about where it would fit into the charges?
What about if the charges were reversed, where the other one had a 1 and the other one had 2. Is there like a difference?
So you're
Would
thinking
they count like as the same?
oops, MgCl2. So you're thinking about something like so, right?
Yeah, would they be considered the same?
I would give them the same priority in terms of charges, and I would go ahead and compare their sizes, yes. And I would not do that to you on a test
Okay.
question, but just in general, I would give these two the same priority, yes.
Okay, thank you.
You're welcome. All right, so other questions so far? All right, so let's go ahead and take our break.